the following video is going to just focus on macroeconomics short-term fluctuations, okay? In the short term, not in the long term. And okay, the idea is just to make several videos in order to explain how short-term fluctuations work in macroeconomics, okay? So this is the first chapter, and we are going to start just with the consumption, a dynamic consumption model, and we are going to just divide it in two chapters. The first one will be the two-period model that we are going to analyze just right now, and then we are going to expand that model to infinite horizon model. Okay, that will be the second chapter. Just to point out how important consumption is for macroeconomics. I just want to say that consumption is just the 60 or 70% of the gross domestic product, so is the most important variable in order to explain the gross domestic product, so it's quite important, okay? And then here, with this chapter of a dynamic consumption model, what I want to point out is just what kind of a relationship is between consumption and income. I mean, the relationship here is that the decision on how much to consume and how much to save, okay? As we receive some kind of income, we have to decide how much we want to consume and how much we want to save. And in this model, that's the idea, to know how much we are going to save, how much we are going to consume, and the optimal consumption level that we must have, taking into account all information that we have if we are rational. Okay, that's some kind of keyword. If individuals are rationals, okay. So yeah, we should also some kind make an analysis when individuals are irrational, but that's more complex. We need more information. We need more stuff. So we are going to start just with the easiest model in order to explain the importance of consumption in macroeconomics and especially in short-term fluctuations. Okay, so let's start with the two-period model. Okay, so let's start with the utility function of the households. Okay, so utility, and this utility is given by this function. Okay. Here, as we are doing like intertemporal decisions, T is for utility. Let's say that we are in two-period models, okay? So this would be like consumption in the first period, and this would be consumption in the second period, okay? Just because we are in a period of two, or in a model of two periods, okay? If it would be like a model with more periods, just it would be the notation would be just t plus 1, t plus 2 till infinity. Okay, so here the utility function has the typical condition, the typical assumptions, okay? Just that the utility is increasing. I mean, we can write it. It's just that, okay, the partial derivative here, by definition, let's put it like, okay, we can put it with E better maybe. Okay, where I is what? In this case, t plus 1. Okay, so here we know that utility is increasing. Okay, another condition and a typical assumption is just what? Let's put it like this, by definition, and this would be the second partial derivative respect to Ci, but also respect to Cj. okay, and this would be smaller than 0 just when I and G is this as above. Okay, what this assumption tells us now that the utility has diminishing returns, okay? So diminishing returns. Okay, and then of course the INADA conditions, okay, the INADA conditions that, as we know, are just limit when c goes to 0, this must go to infinity, and also what, limit when c goes to infinity, that utility of c of course is 0. Okay, so these are the typical assumptions that we must write about the utility function of the households. Okay, so let's start now with the budget constraint that the individual has in this consumption model of 2 periods. Okay, so let's just okay. So now we are going to analyze the budget constraint. And in this case, we are going to have two budget constraints. Okay, the first one. Okay, we know that consumption in the first period plus savings in the first period must equal to wages income in the first period. Okay, because if we receive a wage and income, we can do two things with that income. We can just consume or save. Okay, now what happens in the second period? We know that we have consumption in t plus 1 because we are in the second period now, and what we are receiving, the income now, we cannot save. Okay, the assumption here is that after, when the second period ends, everybody dies and the individual dies and he cannot just save anything. Okay, he has to consume all the income that he has. Okay, so we cannot save. So only we have in the left hand side of the equation the consumption for the second period, and then the income that we receive is just the income that we receive from the second period, but we also receive what? 1 plus the interest rate in the period before, in the first period, and savings in that period. I mean, we are in the income, we are receiving the income in the second period, but then we have a return of those savings of the first period. Okay? Now, these are the budget constraints, but what we want to do is just put these budget constraints in just one equation, okay? That would be the intertemporal budget constraint, okay? The intertemporal. The intertemporal budget constraint. For this, first of all, we have to isolate the savings from the second period. That's the easiest way to do. So we are going to do savings here is just what? Is just consumption t plus 1 minus t plus 1 divided each one by okay. So now if we exchange this saving in the first equation, we get the intertemporal budget constraint. So we have here what? Consumption t plus consumption t plus 1 must equal to wage t plus t plus 1 divided to 1 plus RT. Okay, so this will be the present value of consumption, and this will be the present value of wealth. Okay, so this of income or wealth. This will be the wealth, absolute wealth. Okay, so from here, we need the consumption function. Okay, the consumption function is what is essential here. Okay, so from here we know that CT, okay, the consumption in the first period must be something like this. Well, this, I mean, is better if we put like, oh my god, better like if we put like this. Okay, and I'm going to explain it just right now. And this is for the second period. So we have okay, this will be, all this is just OHT. Okay, so for that we can just compute the consumption function. Okay, and the form of that function would be that one. So consumption in each period depends what? In the real interest rate and also in the life cycle wealth. Okay, but I mean, in the end, the time path doesn't imply here anything doesn't affect, and neither, I mean, the time path of the income does not affect. Just what affects is the life cycle wealth, the aggregate wealth, okay? So that's the thing here. And then another point that is quite remarkable is that consumption is smoothing, okay? So that's quite important for doing the analysis also. Okay, so we can just draw here, for example, I mean, to illustrate it better maybe, yep, we can, well, oh my god. Okay, so here if we have just yeah, let's say consumption 1, here consumption 2, and this would be the budget constraint, okay, the budget constraint, and of course we can compute these ones, just putting consumption 2 equal to 0, this would be and this would be if we put consumption 1 to 0 equal to 0, just okay, just those points, and this is the budget constraint, okay, and the slope, yeah, the slope would be equal to minus 1 plus real interest rate in the first period. Okay, this is the budget constraint, and let's say that we are here. I mean, this would be the optimal point. So this would be the consumption 1, consumption 2, okay, the optimal ones. And here, let's say that we have the level of wealth. So this is wealth 1 and this is wealth 2. So here the difference between wealth 1 and consumption, the optimal consumption, will be what? The savings in the first period. And this would be just 1 plus the interest rate times the savings in the first period. Okay, so this is a kind of analysis that we have. And then now that if we are here, we can identify the consumer like a saver, yeah, savers, and here like lenders. Okay, so this would be the graphical analysis of this two-period consumption model. Okay, now we have to complement the utility function mentioned before with this budget constraint, or just better with the intertemporal budget constraint. Okay, so let's do that now. Okay, so now we have to, we have to analyze the problem of the household. As always, the problem of the household is to maximize the utility function. Okay, so just maximize utility. Okay, when we have here ct plus 1, yep, when we know that utility is what? As we mentioned before, this is the utility, so we want to maximize it. Subject to what? Okay, subject to the intertemporal budget constraint, okay, that we computed, so it's just okay. This is the intertemporal budget constraint. Perfect. So, as always, we can do this. We can do this computation with a Lagrangian function. So we can write a Lagrangian function here, and of course, is the utility ct plus 1 plus lambda, and here we have wt plus t plus 1 plus rt minus consumption t minus consumption t plus 1 to 1 plus rt. Okay, so this is the Lagrangian function, and now just, you know, to obtain the first order conditions, we just need to do the partial derivative respect to ct plus 1 and lambda. Okay, so if we do it respect to ct, okay, what we obtain is just what? The utility function respect to ct, okay, minus lambda equals 0. Respect to ct plus 1, utility ct plus 1, ct plus 1 here, minus what? Minus lambda times 1 divided to 1 times rt, and this would be equal to 0. And just respect to lambda, we get that we have here, well, if we do respect to lambda, this is just the intertemporal budget constraint, obviously, because it's the condition that we put in the Lagrangian as subject to. Okay, from here we get just the intertemporal budget constraint, and from these two, okay, from these two we can obtain the following one, just equaling lambdas. Okay, so I'm going to erase this. And so what we obtain if we put everything equal, I mean the lambdas equal, if we isolate this lambda here and this there and equal them, just what we obtain is obviously this, the utility ct, yeah, ct plus 1, that must equal to what? 1 plus rt, utility ct plus 1. Okay, just I'm going to write all this again. Okay, so that's what we obtain if we put those lambdas equal. Perfect. Yeah. So this is the condition. Okay. So we want to compute the optimal condition zone. So it's quite easy from here, and this would be just the optimal condition. The final optimal condition would be what? The utility CT divided to utility t plus 1 and this equaling what? 1 plus RT. So this is the optimal condition. So now if we know the utility function of the household, I mean if we know it, for example, I don't know, well, a kind of function, the CES function, for example, then we can compute the partial derivative respect to CT, this would be, yeah, sorry, CT plus 1, respect to CT plus 1, and just equaling to 1 plus RT real interest rate, then we obtain the optimal condition. And from here, of course, from the intertemporal budget constraint, I mean, for this condition that we obtain from these two equations and this using also the intertemporal budget constraint, then we can just compute the optimal consumption function for CT, and CT plus 1. And this would be the result that we want to obtain, okay? The consumption for the first period and consumption for the second period. Here, consumption for this first period, second period, the optimal one. That's the important thing here. And what I want to also explain in this graph is that here, if we take the indifference curve, and we have like, well, something like that. Let's say that here is the tangent point, okay? The tangent point. So that would be, I mean, where the point where the indifference curve and the budget constraint just are tangent, there it would be the optimal condition and the optimal consumption levels for each period, okay? Then what would happen if, well, this is just for 2 periods, but we can just expand this model for more periods, okay? As for infinite periods, that would be the infinite horizon, model that it will be explained in the following video.